All right. So thanks to Bert, Ricardo, and Gabriele for setting this up and having me here. So I want to talk about a deep learning solution for the electronic Schrödinger equation. And so when we build AI or machine learning systems, and here are some famous examples from robotics and reinforcement learning, playing Go, then we usually have to answer two questions methodologically. So what is the kind of a mathematical problem that we want to solve? What is the optimization problem? And secondly, what is the learning structure? So what is the structure which will hold the parameters that we are optimizing, such as a neural network, a kernel machine, or something else? And so we are very interested in solving machine learning problems in physics, or in other words, solving physics problems with new machine learning methods. And in this case, the situation is a bit special because often the physics tells us what are suitable choices for these things. So what is the optimization problem? That could be, for example, a variational formulation of a physics problem. And for the learning structure, we often have to respect certain properties that the physics tells us, such as symmetries, invariances that we want to respect for the solution of the problem, and that are a good idea to build in. And so we are working on various various examples at this interface between physics and machine learning, such as statistical mechanics. So, for example, the sampling problem in statistical mechanics, that's something we work a lot on, and also some more recent work in the electronic structure problem that I will talk about today. And so this work was championed by these two gentlemen here, Jan Hermann and Zeno Schätzle. And it's a deep learning solution to the electronic Schrödinger equation. So what do I mean by that? Specifically, we're interested in the time stationary electronic Schrödinger equation, as seen here. So we have a Hamilton operator, which defines what is the system that we want to solve. So essentially, it tells us how many nuclei and how many electrons they have and describes their basic interactions. And then, since we're interested in the time stationary solution, this is an eigenvalue problem, and we want to find these eigenfunctions, so the wave functions that depend on the electronic coordinates, and the eigenvalues, which are energies. All right. So now, as you have surely seen before in other talks of this workshop, there are, of course, many ways to approach the solution of this electronic Schrödinger equation. It can only be exactly solved for the hydrogen atom, but there are many approximation methods in quantum chemistry that are very successful, such as density functional theory, coupled cluster, etc. And there is this whole field of machine learning of quantum chemical solutions that I'm sure you've also seen several talks of, where the idea is, let's take a database of molecules or materials and take atomic coordinates and use one of these methods, such as DFT or coupled cluster, to compute solutions, energies, forces, and then use these data in order to predict new solutions for other molecules outside this database, outside this training set, with supervised learning techniques. And here are a couple of people that have pioneered this field, and many of them are actually speakers in this workshop. And so this is supervised learning. So this is not what we do, but this is very interesting because the state of this field is so advanced now that basically, if you have a suitably large database, then you can make predictions across a certain part of chemical space or across a certain set of chemical compounds. such as small organic molecules, for example. And the accuracies of these predictions will be on par with the theory level you have chosen as an input, like DFT, coupled cluster. So in other words, the additional error you make with this prediction, as long as you don't predict too far away from your training set, is smaller than the error that is intrinsic to your quantum chemical approximation. So, and there is also very interesting work by people like Anatol von Linienfeld, for example, who has found that actually we only need sort of basis sets of relatively few molecules, small molecules, and he calls these amons, atoms in a molecule. So these are little chemical environment that represent the chemical environments that you find in certain sets of molecules, such as small organic molecules. And if you have very accurate quantum chemical solutions for mini molecules such as these, that can get you a long way. So our approach now is to ask, can we replace one of these standard quantum chemistry methods by a machine learning method in order to solve this stationary, time-stationary electronic Schrödinger equation with very high accuracy and hopefully in a more economic way than what we get with standard methods such as coupled cluster or even configuration interaction methods. Okay, and so basically in standard wave function methods in quantum chemistry, we have this kind of this diagram of pain here, which is called the Popel diagram. So we have methods that give us different approximations of different quality to the electronic Schrödinger equation with different accuracy. But if we want higher accuracy, we also have to pay with a more expensive computational scaling in terms of the number of electrons. And this primarily comes essentially from the number of Slater determinants that we consider in these approaches. So essentially the number of antisymmetric functions that we combine in order to approximate these wave functions here. And then there are outliers here. So for example, density functional theory is one such outlier, which is a fairly cheap method, but it can be extremely accurate when used well. And because of that, the DFT is essentially the most widely used method in quantum chemistry. And we believe that by combining quantum Monte Carlo with machine learning, and specifically we use deep learning, but I think also other function approximation methods that are sufficiently flexible would work well, can also be such an outlier in the sense that it's a method that is fairly cheap. I mean, it's not very cheap, something like n to the 4 to n to the 5, but it can be very accurate compared to other methods which have this sort of scaling. And okay, so what's the idea? So first of all, what is the learning problem that we want to solve? So we need a formulation of solving the electronic Schrödinger equation, which is an optimization problem. And the natural choice here is the variational formulation. So if we are looking for the ground state, that means we're looking for the minimum energy, which is minimum over this functional here, which is the energy expectation value, evaluated over a set of functions, of ansatz functions. And these ansatz functions are parameterized somehow by some sort of parameters that we're optimizing. Yeah. So the natural formulation as a deep learning problem is we represent the wave function with a neural network. And this here, this energy expectation value becomes our loss function. Now, of course, in standard quantum chemistry methods that operate with Slater determinants such as Hartree-Fock, etc., the functions, the ansatz functions that go in here are chosen in such a way that these integrals here can be easily and computationally efficiently evaluated. And this is something that we will in general lose when we represent the wave function with a deep neural network, which is a very complex function that we cannot assume to be easily decomposable into contributions that allow us to write this integral in an easy way. So the natural formulation that we get is quantum Monte Carlo, because in quantum Monte Carlo, we replace this integral here by a numerical expectation value that we approximate with Monte Carlo. So we sample electron configurations with respect to the probability of finding them, so the square norm of the wave function. And the quantity that we compute the expectation value over is this local energy, which is Hamilton operator applied to our wave function divided by the value of our wave function. And this is essentially just a function evaluation. So this is something we can relatively easily compute when we have an expression of psi that we can evaluate. So this is basically what we do in every iteration of our training. And then also in every iteration of our training, we have to update electron configurations with respect to this distribution, which can be done with Monte Carlo or Langevin dynamics, for example. In any way, we have an expression of the probability distribution that we sample from with our neural network. Okay, so this is essentially quantum Monte Carlo. In every batch of electron configurations that we sample, we will then optimize these parameters by minimizing this loss. All right, quantum Monte Carlo with neural networks, that's not new. So that has been pioneered by Giuseppe Caleo. He has used restricted Boltzmann machines in this wonderful paper from 2017 in Science in order to represent such lattice quantum systems. And basically used a similar idea where the network represents at the same time the wave function and also allows us to sample from states. Now, we don't have such lattice systems. We have fermionic systems representing the electrons in a molecule. So this is a little trickier. And also, we need a lot of flexibility in our wave functions. So this is why we chose to have deep neural networks. Giuseppe also has a version of these restricted Boltzmann machine based fermionic systems. And this is basically a second quantization formulation where they essentially sample Slater determinants. Okay, so we follow a complementary approach. This is a first quantization approach. So we really sample electron configurations in real space, and we have real space wave functions that we're optimizing. So this approach is most similar to the Fermi-Net approach developed by the DeepMind folks. And these two papers have actually appeared on arXiv the same month, last year in September. What's the difference between them? So we have a different architecture, neural network architecture, which builds in a lot of the physics of the wave function that we know about. The Fermi-Net architecture is essentially a much larger network, but conceptually simpler because it doesn't have sort of these extra features that make sure that only certain functions can be represented that are physically allowed. Because it's much larger, it can also be trained to higher accuracy, but it's also much more expensive. And so I would advocate for this Paulinet architecture because I believe encoding the right physics is important, especially as we go to more complicated systems, as these can be extremely hard to optimize otherwise. And also in the end, I mean, solving this equation, we know which equation we want to solve. So you can always get very accurate solutions if you're willing to pay more. Right? So in quantum chemistry, the question is always, how can I get a certain accuracy with a certain computational cost? Because in the end, doing full CI in the large basis set limit is of course always the most accurate, but in practice you cannot go very far with that. So okay, so this is the equation we want to solve. What are the physics that we want to encode in the solution? So the most obvious and the most important constraint is antisymmetry. So fermionic wave functions are antisymmetric. So that means if we have two electrons of same spin and we exchange them, the sign should exchange. So that means if the two electrons approach each other in space, then the wave function should approach 0, and the probability to find the configuration there should also be approaching 0. So that's the Pauli exclusion principle. And this is, as usual in wave function methods, encoded with Slater determinants. But we have to modify these Slater determinants because we want to use deep neural networks in order to gain something in the representational power. So we have an antisymmetric part here in our wave function. This is our ansatz function, our wave function that we learn. It has an antisymmetric part and it has a symmetric part. And then it has various components here that represent different parts of the physics, of the quantum physics that we want to encode. And I will now go through these in detail. So first of all, the antisymmetric part is implemented with Slater determinants. So we have, the idea is we have n electrons. We have some set of ansatz functions, so orbitals. And we assign these n electrons to n orbitals. And as a result, we get these pairwise combinations. So that's the Slater matrix. And if we compute the determinant of such a matrix, this is an antisymmetric wave function because the determinant is an antisymmetric function with respect to exchange of electrons. However, a single matrix determinant is not very expressive if we use single electron functions here. And for this reason, these wave function methods need a large number of such Slater determinants to get a high accuracy. And then eventually you end up in this exponential scaling if you want to be extremely accurate and use the configuration interaction methods. So what we do here is we use a backflow function. Again, the backflow is not our invention. That's a well-known trick, but it has so far not been used with deep learning. And for this reason, it has so far been of essentially limited expressive power. The idea of the backflow is as follows. We start with our n electron positions in real space, and then we move them through a neural network, so through a function, a feed-forward function, which again outputs n positions. So you can think of these as pseudo electrons or pseudo particles. But the idea is that after this function, these electrons have interacted with each other. So these new particle positions have multi-particle character. So they have information about all of the other particles in them. And because of that, the idea is that if we can train such a function, we can be much more expressive than with single electron functions. And we can get away with fewer Slater determinants and still get high accuracy. Okay, so that's the idea of the backflow. And now we do that with a neural network. Essentially, there's a wide range of choices we could use here for the backflow. One restriction that we have to obey is that the function must be equivariant with respect to exchange of same spin electrons. So whatever function we learn here, it has to be such that if we exchange two same spin electrons at the input, the corresponding outputs also have to exchange. So the corresponding pseudo particles also have to exchange. And here we use a graph neural network, which is derived from Schnet, in order to implement this backflow function. I won't go into details right now about this network, but I'm happy to answer questions about that. What else do we do? So now we don't want to learn very basic physics from scratch. So what we do instead is we say the elements of our Slater matrix are actually composed of Hartree-Fock orbitals, or multi-reference Hartree-Fock if we use multiple determinants, multiplied by a function that we learn. So actually the backflow function is multiplicative. Yeah, and that ensures if we initialize this function properly, so that it's close to 1 in the beginning, then we will start with the Hartree-Fock solution, which is at least a more or less reasonable solution. Then we learn essentially corrections to this with deep learning. So we learn this backflow function here, f, which goes into the antisymmetric part. And we learn a symmetric function, the Jastrow factor. If we have an antisymmetric function and we multiply it with a symmetric function, we still have an antisymmetric function. So this maintains antisymmetry of our wave function. So basically the idea is to exploit the flexibility of deep learning for these functions here to achieve higher accuracy. Finally, the asymptotics. So we know that ground state wave functions have certain asymptotic behavior as electrons approach each other or as electrons approach nuclei. The derivatives of the wave function go to certain limits. And it's extremely important to build in these asymptotics into the solution because they're very hard to learn. In these limits, the probability to find electrons there can be very small. So sampling them in a quantum Monte Carlo approach can be a rare event. And then we can get suddenly or occasionally very, very high gradients or high forces if we don't force the asymptotics to be right. And that would be extremely bad for our optimization. And to avoid that, we build the right asymptotics into these functions here, into the nuclear cusp and the electron cusp correction here. So again, the functions that we learn, the neural network functions that we learn, are cuspless in the sense that they do not change the cusps in these asymptotic limits. So these are essentially all the components that are the ingredients of PauliNet. And this is a diagram where you see just in a diagrammatic form what is computed in this function. And all the green functions here are fixed. They are just in order to ensure the right physics, whereas all the orange functions here or arrays are learnable. So this is what's trained as a deep network, or here just arrays, as part of the stochastic gradient descent optimization. Okay. And so let's see this in action. So let's start with some simple toy models. These are just 1 or 2 atom systems where we can basically get arbitrarily accurate results with existing methods. And so what we are plotting here is the correlation energy. So correlation energy is the difference between the Hartree-Fock solution and the exact solution, where exact here is some CI method in the large basis set limit usually. And then here we just plot essentially in a logarithmic axis the error, or 1 minus the error, 100% minus the error. Yeah, so every decade here is essentially 1 order of magnitude more accurate. So you can see here that how the accuracy increases with the number of quantum Monte Carlo steps, iterations. And these plots here on the left are with one matrix determinant. So that's a single matrix determinant, a single Slater determinant solution. And here you see the solutions with 6 determinants. And here you see just training the Jastrow factor. Yeah, so that means we keep the Hartree-Fock orbitals and we just train a symmetric modification of it. That's what's usually done in variational quantum Monte Carlo. And here we switch on the backflow. So we additionally have this nonlinear training of the orbitals. Right, and you see that both things help. So using the backflow helps us get more accurate. Using more determinants also helps us get more accurate. So comparing to other quantum Monte Carlo approaches, this is how we compare. So what we plot here on the x-axis is the number of determinants. And in some of these functions, these are not, some of these methods are not using single determinants, but they use configuration state functions. Configuration state functions are groups of determinants that are varied together. And as a rule of thumb, these correspond to about 10 times as many determinants if you count determinants. So you can imagine essentially switching these open bullets 1 order of magnitude to the right here, then we are about in the same in the right regime of complexity or how many determinants we use. And the bottom line here is that the Paulinet solutions are on the top left of these plots. That means if you use a few determinants only, you can get a very accurate solution for which you would need significantly more determinants without training them with deep learning. And here you see this a little bit more clear. This is using diatomic molecules. Again, on the x-axis, number of determinants or configuration state functions. Configuration state functions, again, should be about 1 order of magnitude to the right. But it differs between different methods, and we do not always know how many exactly. So we just, this is just qualitative here. But roughly, you see that with about 2 orders of magnitude less determinants, you get comparable accuracies for these simple systems. Okay, can we also do something interesting for non-trivial systems? So a nice toy system for that is the hydrogen 10 change. That's a strongly correlated system, especially as you stretch the chain. So that means you typically need many determinants with a standard method. Or you need to really build a method to do this well. And what we report here is basically the results of Paulinet with 1 determinant without backflow, 1 determinant with backflow. So that gets us to about 97 to 98% of the correlation energy. And then with 16 determinants, that gets us to 98 to 99%. And this is compared to specialized methods that were really designed to solve this H10 method well. We're using the same Paulinet that we've used for the single or diatomic molecules. Yeah, so this is not tailored at all for this method. It's out of the box. Okay, and we get approximately similar accuracies for different distances or bond lengths between the hydrogens. So even as we go to the more electronically complicated case, we have a similar accuracy with a similar number of determinants, with the same number of determinants. Okay, this is my last slide. So here's a perhaps chemically more interesting systems because it's really hard to solve the standard methods. So this is cyclobutadiene, still not a very large system, 27 electrons. But this is essentially too hard for standard coupled cluster methods with singlets, doublets, and perturbative triplets, which is a very good method for small molecules in general. So what you see here on the left is the absolute so the total energy, the variational energy, and it's variational energy with our variational approach. It's not variational with coupled cluster because coupled cluster is not a variational approach, but so that's the total energy. Hartree-Fock is of course hopelessly off here, and that's because we go through this very electronically complicated intermediate state here. Then we have the coupled cluster results, which are still tens to hundreds of kcal per mole too high. And this here is these here are the energies that we get with Paulinet as a function of the variational Monte Carlo iteration. And what you see here is the energy of the minimum configuration and of the transition state energy. Now, if you compute the difference between those, this is what we are more interested in here than the absolute energies. Then with a standard coupled cluster, singlets, doublets, triplets method, we are quite off here. We get about 20 kcal per mole. The experimental value is in the area of 10 kcal per mole. And with a specialized multi-reference coupled cluster methods, we get into this regime. Then depending on the exact variation of that, you are a little bit, you get a little bit different results, but you're around this 10 kcal per mole that you also get from the experiment. And this is also what we get with Paulinet. We get that with the same Paulinet again, which has been used with 1 or 2 atoms. So this is not specialized to this system at all. It's just essentially trained on a new Hamiltonian. And it scales it. So first of all, in absolute time, we have an absolute a similar computational time than needed for these multi-reference coupled cluster methods. But of course, using a code that is not highly optimized. And also our scaling, our asymptotic scaling is n to the 4, whereas these coupled cluster methods are n to the 7. So we hope with this sort of approach, we can go to significantly more electrons, maybe 100, 200 or so, and then get really high accuracy solutions there. And then I think it would be very interesting to use these results for example, Gaussian process or kernel methods in order to predict across chemical space. All right, and with this, I'm finished with my talk. So I'd like to thank my co-workers, especially Jan Hermann and Zeno Schätzle, who have been the main protagonists in this work, and the funders and collaborators, and you for your attention.
Thank you. Thank you very much. So the floor is now open for discussion. Let's see if there are some questions. Gabor.
Hi,
Gabor.
thank you, Frank. Very beautifully clear talk. Can you remind me how the scalings compare with not the sort of classical quantum chemistry, but things like the FCI QMC that a lot of benchmarks were done for these diatomics. I'm not sure about the cyclic routine, but
the scaling in terms of the number of electrons. I mean, FCI in principle is exponential.
No, FCI QMC. You know, this sort of Ali Alavi.
You mean Ali Alavi stuff? Yeah.
Not just the scaling, but the sort of absolute runtimes and accuracies. Because that's
so I'm not an expert in this, but you typically need to sample a huge number of determinants with this approach to get similar accuracy, like tens of thousands to millions.
They have some dimer results, and I think it will be interesting to see because. Okay, the other question I have is you quote a scaling, but does that scaling include the expected increase in training, quote training time. I know that there's no supervised. I mean, but the stochastic gradient descent time as the number of electrons goes up, or have you not been? Have you been measuring? Have you been looking at that?
So this is why I was a little bit vague about whether it's n to the 4, n to the 5. At the moment, it's actually n to the 3, what we're doing here empirically, because we're not yet at a level at a number n where essentially the higher cost kicks in. N to the 4 is for standard VMC, and that's including the training. Now here, you could argue the training is probably different because we use stochastic gradient descent, and who knows what's happening, right?
That's right. Yeah.
So we expect to be somewhere in that range for the essentially number of electrons that we're targeting. Of course, we're not targeting systems with 1,000 or 10,000 electrons here, but I can't give you a mathematical proof.
Okay, but the answer is that the n to the 4 is the kind of formal scaling.
Yeah.
And it'll
That's right. So the n to the 3 would be from essentially computing the determinants and then another n from the optimization.
N to the Hartree-Fock is n to the 4, right? And you take that as a baseline. So
okay, that's also n to the 4 for getting the initial result. That's true.
Yeah. Okay. Sure. Thank you.
Okay. Any other questions, Anatol?
Hi, Frank. Great.
Anatol, good to see you.
Well, I'm hidden. Anyhow, just a very practical question. Effectively, can you already sort of give a quote on how expensive it was to do cyclobutane or the H2 chain, or I mean, what are we talking here? Thank you.
So cyclobutadiene was 40 GPU hours for 0. That's about the same as you pay for these multi-reference coupled cluster methods. But of course, there are many tricks you could do in the code to make it more to reduce the prefactor. So, for example, we don't do things like speeding up the computation based on the fact that many of our slated determinants share many columns and rows and things like that. For the small system, it's basically minutes on a single GPU. This is all single GPU, so it's fairly okay. And so for Ferminet, if you compare to Ferminet, they train on 8 V100 GPUs. So we use 1080s. So V100 is maybe factor 2 or 3 faster. And they train on 8 of them in parallel for something like 2 days or so for the small systems. So it's a lot more expensive. They do get a somewhat higher accuracies too. But I guess we can also push the accuracy a bit when if we would increase the network size. But that gives you an idea, I hope.
So I was actually going to ask you a question about that. So I thought that you said bringing in the physics is very important. And also the deep neural network actually maybe don't have to be so deep because we can do some kernel methods or something like that. But now you're saying actually the deeper the better, or is that not true?
So I'm not sure how deep you need. So our network is basically 3 layers deep. So this equivariant interaction block here, that's essentially a 3-layer deep graph neural network, right? And then this backflow and Justro, that's just 1 layer. That's just 1 output layer. So it's not a very deep network. But of course, you can make the layers wider. You can just use many more parameters.
But I thought you were saying that bringing in the physics is actually essential. But now you're also saying that actually this Fermi solution is gets actually better performance by just having a deep network. So are you saying it's not essential to get the physics right? Or is that...
No, I think if we compare at similar runtimes, we probably have better results, but it's very difficult to exactly point the finger on that without actually having both codes. And at the moment, the Fermi-Net code is not available. But that's what it seems like from the paper. So what is clear is that one of the main contributors to their computational expense is that they use a second-order optimization method. And that's because with the first-order optimization method that we use, their network doesn't converge well. Convergence is very slow. And it remains to be tested, but I believe this has to do with the asymptotics. If you don't build the asymptotics in, you get pretty bad forces initially, and also maybe starting from the Hartree-Fock solution can help.
Yeah. Okay. Thank you. There is, in view of time, there is one more question from Florian.
Yeah, I just wanted to ask: is it conceivable in the future that you would have a second network that is supervised, trained to guess, given the nuclear configuration, what would be a good first guess for the network weights inside your network, so to speak, a first guess for your wave function, and then you start the variational stuff?
For the network weights is hard because there are many of them, but for the orbitals, I could imagine that instead of using just Hartree-Fock orbitals, doing a supervised learning prediction of the orbitals and starting from there, that I could imagine, yes.
Thank you.
Okay, well, thank you very much, Frank.
Thank you.
For this illustrative talk.